Okay, so it's 4 o'clock. We can get started. Welcome, everyone. These Tuesday slots are reserved for seminars by IUCAA members. So today we have Vishal Upendran, who is a research scholar here at IUCAA, telling us about the formation of solar wind and switchbacks and quiet sun heating. Vishal, please go ahead.
Thanks, Asim. So, hello everyone. So, I am Vishal Upendran and I am a fourth year student working here with Professor Durgesh Tripathi. And so, I'll be talking to you, as he mentioned, on a recent paper on the formation of solar wind, switchbacks, and quiet sun heating. So, before we start, let us recapitulate what happened last week. So, last week we had crazy weather here with the sun playing hide and seek, and it was actually missing in action. By the end of Sunday, everybody was yearning for the sun. Give me my sun back. But if you look at a typical day, this is from an image. I took this image from my room many moons back, and this is what you see as a sun, right? What you see here is called the disk of the sun, which is what people across cultures have been praying to and whatnot. Now you can zoom in to this particular image and look at what the sun looks like in close up. And don't use a telescope to look at it through directly through your eyes, just project it on a wall or something. But if you sort of zoom in into this image, what you find, this is a solar disk, sort of looks like a very plain image, but with a couple of these black spot-like structures occurring everywhere. Now, this disk, as we have been calling it, is what is called the photosphere. The photosphere is a region of the sun from where the photons are free streaming and they just escape and sort of come to our eyes. These photons are at a temperature of around 5,500 degree Kelvin. And you can also further, if you're zooming into the disk of the sun, you may as well zoom into the structures that you see in the sun. So we can essentially zoom in on these two dark spots present here. These two dark spots are called sunspots. And what you see here is that this is not some really simple structure at all. You find these dark structures and sort of grayer structures, and you have this white noise-like type structure all over the sun. So the sun, if it looks, it might look very simple from very far away, but when you zoom in, you can continuously see a lot of structure emerging out from just this photosphere itself. But the photosphere, as I've told you, is just from the surface from where the photons start to be free streaming. But you can look at various layers of the solar atmosphere. So this disk is called the solar disk, and what you have outside of the disk is called the limb. So off-limb structures are found somewhere outside the sun, and these correspond to structures which form much higher in the solar atmosphere. So if you look at just this sunspot pair, let's say, and look at how it and see how it looks like at different heights in the solar atmosphere, we see that the structure is extremely rich. The yellow-orange kind of image that you have at the bottom corresponds to the sunspots that I've shown you earlier. But you keep probing the same region, same field of view at different heights, you see that this structure sort of becomes very dark, and you have these tiny granule-like structures. And then this, as you keep probing higher and higher, you keep seeing small loop-like structures, and finally, you have these extremely large loop-like structures which are connecting various parts of the sun. Now, this is an extremely rich and complicated structure of the solar atmosphere as you keep probing various sites. The solar atmosphere itself is also very interesting and very complicated to study because of its temperature profile. So this solid line that you see here is the variation of temperature with height from a model. And what it basically tells you is that as you move away from the photosphere, which is at height equal to 0 to greater heights, the temperature keeps increasing and sort of increases to more than 100 times the photospheric temperature. It increases to around 1,000,000 degree Kelvin. And common sense dictates that if you have a hot object, and if I'm moving away from a hot object, the temperature should drop, but the opposite is happening here. And this, based on the kind of typical temperatures in these different regions, astrophysicists have given names to these various structures. So you have the photosphere, which is at around 5,500 to less than a 4,000 degree Kelvin. And then you have the chromosphere, which is around 10,000 to 30, 40, 50,000 degree Kelvin. And then you have this very thin layer called the transition region, where the temperature suddenly rises from 10 to the 4 Kelvin to 10 to the 5 to 10 to the 6 Kelvin. And then finally, you have the solar corona, which forms at much higher temperatures. So what is the effect of this kind of a temperature profile and density profile? what we basically get is that different ions form at different temperatures, approximately, and these give rise to characteristic lines which probe a given height in the solar atmosphere, approximately. And what structures you see are basically corresponding to the concentration or the abundance of these ions in these different structures. So if you were to map the image on the left of these various slices to this model on the right, it would be something like this. So these different images are probing different heights and also probing different temperatures. So on an average, we can have a one-to-one correspondence between temperature and height in the solar atmosphere. And different ions are dictating what's happening different ions are probing what is happening in these different heights. Now, what dictates what is happening in these different layers? So that requires something called plasma beta. So plasma beta is the ratio of gas pressure to the magnetic pressure. And plasma beta is a proxy for telling us whether the gas motion is what is dictating the dynamics of the plasma, or is it the magnetic field dynamics that's dictating the dynamics of plasma. So if plasma beta is more than 1, it means that flows in the photosphere, for example, will dominate what is going to happen to the plasma. But if a plasma beta is less than 1, it means that whatever the stuff magnetic field is doing, for example, reconnection, that is going to dominate what is going to happen in the atmosphere. One consequence or so of this is that if you look at high in the corona, let's go back to these loop-like structures that you see in the corona. These loop-like structures basically trace the magnetic field lines because the plasma is frozen in these field lines. And approximately you could say that the field lines are connecting from one end to the other end in this fashion. Of course, we have a lot more radiative transfer complications that goes on here, but approximately mass follows magnetic field in the corona. So these different regions that we have been differentiated the atmosphere in also have different dictating terms as to what gives rise to the dynamics. The chromosphere is much more complicated because the plasma beta is changing from more than 1 to less than 1. So it displays a very rich set of structures and properties which are extremely difficult to study. And finally, you have the solar event, which is basically a stream of particles, which we'll see later. And here the plasma beta is more than 1. But these individual structures are not like individual monolithic structures. There's a constant exchange of mass and energy across these various parts of the atmosphere. One interesting example that we have is what is called a jet. So you can see this image that the plasma is starting to rise up, but keep looking at where I'm swinging the red pointer, and you see that there is some plasma that's starting to rise up, and you see this tornado-like structure coming out. So it's basically like a volcano that's shooting out jets of plasma into the atmosphere. And this way, it gives mass and energy across various layers of the solar atmosphere. Now, what I've shown you here is basically that the length scales involved are more than 50 megameters. But and they're a part of an active region, if I'm not wrong. And because of the complex magnetic field dynamics, we give rise to such large jet-like structures. But how do we know that the magnetic field dynamics is giving rise to these jet-like structures? This is another movie of jet here. Look at the image on the left side, where you have the dark stuff. So you see the dark stuff is evolving, and then you see the jet forms now, and the plasma is coming out. So this is a typical jet that you see on the disk of the sun. This is like face on. The image on the left, which shows AIA 304, is on the side of the sun. It's called the off limb. Now, if you consider the face on image here, and the corresponding image on the right side, which basically tells you the magnetic field, where black is negative polarity and white is positive polarity. Look at the red box, and let's wait for the animation to start. Yeah, so you see that there's some white flux there, and there's a black flux there. And as the jet evolves, keep noticing that the black stuff starts to go away, and now the black stuff is almost gone. The black polarity is almost gone. So interaction of these opposite polarities of magnetic field and the dynamics that is associated with them is, so this magnetic field is measured in the photosphere. So this interaction in the photosphere is actually causing some effect in the corona, which is like much further up and is at a very different temperature. So you see the kind of coupling that's going on in the solar atmosphere. So these are large structures. We can look at much smaller structures. So these are called spicules. So these spicules are again jet-like structures where it's like basically a burst of energy that's just being dumped upwards. So plasma is just thrown upwards, and it may come down and just go into the atmosphere. So anything can happen with it. And here it shows the animation shows an off-limb structure with these speckle-like motions happening across the whole of the disk. And this is what is called a quiet region, where you don't have very complex magnetic field, like a magnetic field structure, but it is rather simpler to study. But even here, you see that the kind of activity that's going on in the atmosphere, this continuous exchange of mass, mass is going up and coming down. And, but the length scales involved here are only a couple of megameters, like 10 megameters or so. And what is it? So is it like that does the magnetic field dominate the dynamics of these specules too? Apparently, yes. So in this paper by Tanmay Samantha, what they show is that the blue color contours correspond to the magnetic positive polarity, the negative polarities, whereas the red color contours correspond to positive polarities. And these black lines that you see are basically specules, which are when they are seen on disk. So these black lines are basically similar to these jets upflows that you see here. And interestingly, if you look at all these circles, small circles that keep popping up, when two opposite polarities are interacting, you see the specules are sort of starting and going out. So even if your length scale is 50 megameters or 10 megameters, you still have interaction of magnetic fields or magnetic field dynamics giving rise to this mass and energy exchange. And that is very interesting. So what causes this mass and energy exchange? So this is what is called a granulation pattern. So this is from Avetana's thesis. So what you see on the right panel is the line of sight velocity. So basically blue is towards you. So blue is towards you, red is away from you. And what you see is basically these granule-like structures, all these small dabbas. The center of these granules are basically blue shifted and coming towards you. The corners of these granules are red shifted and moving away from you. And what this does is that so this is in the photosphere again. So in the photosphere, the plasma beta is more than 1, which means that the gas dynamics is being dictated, the gas pressure dictates the dynamics, which means all these granular flows is what is dictating what is happening to the magnetic fields. So all these flows that go outside and sort of come back down, that is what is causing all sorts of stuff with the magnetic field. So what is the consequence of this kind of a motion? What happened? There are two things that happen. First thing is that the magnetic field lines are buffeted around because of these flows. The second thing is that magnetic field lines are concentrated because the flows sort of push the magnetic field lines away and they move and concentrate towards the dark lanes. So in this G-band image here that I show you on the bottom, you see these bright structures within the lane-like regions. So these bright structures are basically concentrations of strong magnetic field, which are coming because the magnetic field inside the granule is being just shifted away into the granules because of these flows. It just gets extremely concentrated and it's also being buffeted around in like a random walk. So then the basic question we can ask is, we have seen that the photospheric motions are sort of affecting what is happening in the corona. So is it something similar also happening here? Do these buffeting motions cause something in the corona? So the answer is actually yes. So there's something called field line braiding. So what was proposed by Parker in 1994 is that if you take two surfaces and have like a parallel field, magnetic field between these two surfaces, keep the top boundary fixed and perform a random walk of the bottom boundary for each field line. What this does essentially does is like it acts like granules and it sort of mixes up all of the magnetic field and sort of tangles them up. What happens because of this, a consequence of this tangling of magnetic fields is that it gives rise to excess currents in the system. When you have excess currents, the magnetic field lines can reconnect and release free energy. And once this free energy is, note that that the tangling motion is happening in the photosphere, but the tangling is happening all over the solar atmosphere and possibly more in the solar corona. So if you have tangles in the solar corona, and if they are being released by magnetic reconnection, then the energy is being released locally into the plasma. And what this does, it raises the temperature of the plasma there and maintains the temperature and maintains the corona at 1,000,000 Kelvin. So this was a kind of mechanism that was proposed by Parker to explain, or to give a viable hypothesis as to why the solar corona is hot at 1,000,000 Kelvin. And this is something we have seen through simulations too. So this is a simulation by Vigo, Hanstein and others, where they have a bunch of magnetic field lines and they are being buffeted around by the photospheric motions. And what they basically find is that so the bottom panel is the temperature, and the temperature is in log scale, and the red color corresponds to log T of 6.2, so it's 10 to the 6.2 Kelvin. And what they find is that the so the longer loops correspond to sort of higher temperatures, and this kind of shuffling of foot point gives rise to these large temperatures. So one basic signature of these shuffling motions is the presence of what are called impulsive events. So these impulsive events are bursts of energy which occur everywhere. Or the hypothesis is that these impulsive events occur everywhere, all over the solar corona, and sort of maintain the temperature at 1,000,000 Kelvin. And the way one infers the presence of these impulsive events is through spectroscopic studies. They look at the temperature, the velocities, the emission measures, and stuff like that. But do you actually see impulsive events? So this is through simulations and so through the theoretical side. But do we actually see any impulsive events at all? So the answer is yes. There is a lot of work on impulsive events, but I'm showing this in animation because it's very recent work. So the top 3 rows and the bottom 2 rows correspond to the extreme ultraviolet intensity images, and they are corresponding to the coronal images. So what they find, look at the green box, you see that there is that impulsive brightening that's occurring, that's being seen in all the panels here. So the length scale involved here are only a couple of megameters. These are a couple of pixels wide. So I think there are just a couple of megameters. But if you look at the corresponding red box here in the magnetic field, again, black is negative polarity, white is positive polarity. You see that there is an interaction of magnetic fields happening in the photosphere, and slowly that black field line, the black field patch sort of goes away, and then just the white patch remains. So you see that the interaction of magnetic field, regardless of the scale, if it is 50 megameters or 10 megameters or 5 megameters, interaction of magnetic field is giving rise to these kinds of different kinds of events. And these small scale interactions are giving rise to impulsive events, which are occurring at multiple locations on the sun. So then a logical question we can ask is, what happens if we just look at like one pixel? Because each pixel has an intensity. So you can always ask, what happens if I just take one pixel and try to understand how the intensity in that one pixel comes from? So this is a work which we did sometime early this year, wherein we assumed an impulsively heated light model, and we checked, and we were asking if a given light curve from a single pixel can be explained by such impulsively heated models. So the orange light curve in the background corresponds to the observed light curves, whereas the blue light curve corresponds to the simulation, the best fit simulation, if you want to think about it. Visually looking at these two light curves, you really can't say if they're good or not. But if you look at the intensity histogram from the CDFs, we find that the observed light curves are matching very well with the simulated light curves. And so is the case if you consider the wavelet power spectrum. So even on a pixel scale, so each pixel here will correspond to something like 700 kilometers or so. So each pixel also is explainable through an impulsive heating scenario, which occurs due to dynamics of the magnetic field in the photosphere. So this is at a pixel scale. We can also look at the sun globally, right? So the sun is not just limited to a couple of pixels. So we have a lot of stuff happening globally in the sun. So this is an image of the outer solar corona. So this is again the solar corona. So the magnetic field is dictating all the dynamics in this region. And there are some important definitions here which you must take care of. First is these dark structures. This dark structure here and here. These are called coronal holes. These are called coronal holes because they appear to be holes in the corona. And if you look at the plasma that's going up here, you see that the plasma is going out radially, and it's sort of, which means that if it is tracing the field lines are going out radially. And if you wait for the animation to come back, if you keep looking at this space where I have the pointer, you'll see that it also releases plasma periodically into the sun, into the interplanetary medium. So you see now, I can see that, there's some plasma has gone out. You can see that plasma is coming out. So these open field lines act as sort of a guide field, if you want to think about it, to guide the plasma away from the sun and fill it in the heliosphere. Now that is not the only structure we see here, right? You also see these bright structures here. These bright structures are called active regions, and these active regions are extremely complex, magnetically complex regions which have close field lines. And we will not study them now because it's not a part of the work. But if you want to think of solar flares, a lot of solar flares occur in active regions. And the third kind of region, but actually you should not think of it as a third region, but it's the background, is this region called quiet sun. So this quiet sun is the background over which we find if there is an intensity enhancement in active region or an intensity deficit in the coronal holes. So this quiet sun exists regardless of the solar cycle. It always exists, and that is like kind of a benchmark over which we perform every other study. Now, this large loop-like structures that you see emerging out from the sun, they also interact, and you see that there's some stuff that's coming out. So periodically, this interaction gives rise to a lot of plasma being ejected from the sun into the heliosphere, and this is what and this is something that keeps going on for all the time. So it's not something that occurs only at certain periods of time. This occurs all the time. The sun keeps ejecting plasma, and when it ejects plasma, it's what is called the solar wind. The solar wind is a stream of particles that starts from the sun and fills the interplanetary medium. The solar wind sort of interacts with the Earth's magnetosphere and gives rise to various space weather effects. One of these space weather effects is what are known as aurorae. Now, this solar wind, so whatever ejection that you saw in the previous animation is also, so these are not small, these are a couple of Earths, if you want to think about them, in size. And they sort of just bam and hit the Earth and cause various geoaffective storms and stuff like that. The solar wind itself is interesting in that there was a recent it's a discovery in the solar wind that you have what are called switchbacks in the solar wind. So if you can see, let the animation play again, you can see these S-like structures which are sort of present all over in the solar wind. So these S-like structures basically are rotations in the magnetic field. So if you can see in my video, we have this S-like structure here, and if you have a spacecraft that goes perpendicular to these structures, what it finds is that the magnetic field strength, mod B, remains constant, whereas the radial field sort of flips sign when it passes through these S-shaped structures. So these are called switchbacks in the solar wind, and they were found by Parker Solar Probe as it was going towards the sun. And the origin of switchbacks is not very well known. As do they form somewhere in near the sun, or do they form somewhere in the solar wind itself? Is it in situ, or is it being propagated outwards? So in that sense, this animation is a bit misleading because it tells you that it starts from the sun and goes away. But then we'll see how this observation can also be explained by the analysis we have. Now the question, one of the main questions, the first question we ask is, what is causing the coronal heating, the heating of the solar corona? Are impulsive events viable or not? So that is one question we always ask. The second question we are asking is, where does the solar wind start? What are the origins of the solar wind? In 1990s, or since 1990s, there has been a lot of evidence that the coronal holes, which were these dark structures in the solar corona, are very well associated with the solar wind speed. And so this tight correlation has been seen over multiple observations for multiple rotations of the sun and over extended periods of time. So this is a very well-known strong result that the coronal holes are well associated with the solar wind. And it makes sense because these plasma is coming out in open field lines, and it can easily escape when compared to other regions. Now, we also had another work sometime last year, wherein we had a deep learning model, and we asked this deep learning model for this given prediction of solar wind speed, which region in the sun is most important. And this model told us, 4 days before prediction, the coronal holes are more important. And if you just do a heuristic calculation of distance by speed, this predicted speed corresponds to around 4 days of travel time from sun to earth. So this was very interesting observation for us. But it also told us that, the coronal holes are extremely important, but the active regions are possibly also important, slightly important. But this is like some 6-7 days into the past. So not just through direct correlation analysis or something, but even if you consider a deep learning model which is not being fed in this physics at all, can figure out that the coronal holes are extremely important for solar wind speed prediction. So this mapping between the coronal holes and solar wind is well established in the community. Now, when I said that, when you generally study these different features of the sun, you want to study them with a benchmark. So the benchmark we have is the quiet sun. And the quiet sun is extremely interesting because of this reason. So if you consider the temperature goes down from left to right, I show a series of images. Temperature goes down from left to right, and temperature is right, and the temperature increases with height. So even the height goes down from left to right. If you look at the corona, you see that the coronal holes are dark. The quiet sun is bright in sense it's brighter than the coronal holes. And I don't need to tell you this green contour here to tell you that this is coronal hole, that is quiet sun. You can easily differentiate it if you just look at it. But if you probe ions which are forming much lower in the atmosphere, for example, silicon 4, this image tells you that the coronal hole and quiet sun are not very different. If I don't give you this green contour, I don't think you can differentiate coronal holes and quiet sun from each other. There is not a lot of you really can't differentiate between these two regions. If you probe even lower in the atmosphere, for example, in the carbon 2 line, this difference is absolutely gone. You can't find any differences whatsoever. And in magnesium K3, the coronal holes and quiet sun look extremely identical if you just look at them visually. So this is a very interesting result. This is a very interesting observation, rather, that you have these two regions which appear very similar, very low in the atmosphere. But only if you go very high in the atmosphere that you see there is a stark differentiation between these two regions. Why does that occur? And among these two regions, one region is bright and hot. The other region is not as hot, but it gives rise to a lot of solar wind. So then there's a very straightforward question you would want to ask is, visually, there are these differences and similarities between coronal holes and quiet sun. If we understand why this differentiation occurs and why some things are similar, can we understand the coronal heating problem and the solar wind emergence? From what height does the solar wind start? Can we understand these two questions or not? So it's not like we are the first people to do this. We are standing on the shoulder of a lot of giants. And what people have generally done is they take in a region of quiet sun, a region of coronal hole. They sum up the intensities in these two regions. And then they look at what the difference in the intensities are for different lines. So approximately in solar atmosphere, each line forms at one temperature. And for different lines that have been denoted on top here, from silicon 1 to iron 8 and neon 8, iron 12 and neon 8, we can calculate this difference in intensities. And just look at the stars, don't look at the diamonds. Diamonds are not relevant for us. So what Stuckey et al. Had a series of papers discussing this whole set of results. And what they find is that within the uncertainties, for ions which form at less than 10 to the 5 Kelvin, for example, the coronal hole and quiet sun intensities are not very different. They are very similar. And that is something we have visually seen from the previous slide, from the previous observation. They're not visually they're not very different. But if you look at some ion like neon 8, and if you look at put the average uncertainty error bar, so that be something like that, and you clearly see that the coronal hole intensity is much lower than quiet sun intensity. So at high temperatures, you find the coronal hole intensity to be lower than quiet sun intensity. But at lower temperatures, you find that if you take an average, the intensity differences are not quite seen. But why do you just stop at the intensities? You can also look at the velocities. So yeah, you don't find much differences at the lower temperatures. If you now look at the velocities, what you can see is that the coronal holes, so if you look at the lower temperature ions, within the error bars, the coronal hole velocity, average velocity is very similar to the quiet sun average velocity. There are not much differences there. But if you look at these hotter lines like neon 8, magnesium 10, you can clearly see that the coronal holes are more blue shifted when compared to quiet sun. So blue shifted means the plasma is coming out towards you. So plasma is going like that towards you. And these regions were near the disk center. So if plasma is coming out towards you, and if it's coronal hole, which means it's open field lines, which means plasma is coming outwards from the sun. So clearly at greater temperatures and greater heights, you see that the plasma is preferentially coming outwards in the coronal holes when compared to quiet sun. And this is a physical result which tells us that this plasma is basically the solar wind that's coming out from the coronal holes and sort of then fills the interplanetary medium. But this is just the gross properties, just compare the average values in different regions. But what happens if you look at the magnetic field? So if you look at the magnetic field, this is from Don Hassler's paper, where they look at the neon 8 line. So neon 8, we saw earlier that the last point was neon 8, which showed the differentiation. So in neon 8, if you look at the quiet sun on the left and coronal hole on the right, clearly a differentiation in the intensity is seen. The coronal holes are darker when compared to quiet sun. The black lines outlined on these two images are what are called the network regions. Network regions are a proxy for the photospheric magnetic field. But if you now look at the velocity, again, you see that the coronal holes have excess blue shifts when compared to quiet sun. These two results are again, seen in the previous slide by the two other authors. But here's an interesting result. The the network regions have a correspondence with the excess upflows. So all these strong upflows that you see are sort of related to the network regions, and this is seen in both coronal holes and quiet sun. So it means that there's a strong field region is doing something to the flows, and that must be studied in detail. And so this was taken up further by two and others, where they looked at the velocities of a coronal. So this is a coronal hole. We looked at the velocity of neon 8 line in a coronal hole and sort of asked which property of the magnetic field is well correlated with this coronal hole. So they found out that the inclination of magnetic field at the formation height of this ion is very much related to the velocity, is well correlated with the velocity of the ion. And so they found out through extrapolation that you have these funnel-like structures that sort of come out. And within these funnel-like structures, you have excess blue shifts. And you can see very clearly that you have some blue shift at lower heights. And as you go out also, you have these blue shifts persisting. And so this plasma is just starting at some low height and it's just coming down and it's going up as a solar wind. So what they find is a solar wind, even in a coronal hole, it's not like the solar wind is just coming out all over the place. No, the solar wind is coming out from very specific structures called the coronal funnels, which are sort of guiding the plasma into the solar atmosphere. So this is again a gross differentiation, but so the two's work is basically just analysis of the coronal holes. But can we compare coronal holes and quiet sun as a function of the underlying magnetic field and see if you can see some differences or not? So this was done by Durgesh and collaborators sometime early this year. So what they did is they took the silicon 4 line, which is forms at the lower transition region, and look at various properties of the silicon 4 line in coronal holes and quiet sun as a function of the photospheric magnetic flux density, and try to see if some differentiation is seen or not. Now, remember we had seen the silicon 4 line earlier, where no differentiation in a gross way is seen between the two regions. But what Durgesh and others find is very different. For a given magnetic field bin, they find that the blue color, the coronal quiet sun, has excess intensity when compared to coronal holes. So the differentiation in coronal holes and quiet sun is seen at the silicon 4 formation heights or silicon 4 formation temperatures. But this is only seen if we consider the underlying magnetic field distribution. Otherwise, it is not seen. And similarly, also look at the average velocity and find that the quiet sun is on an average more redshifted when compared to coronal holes for a given magnetic field bin. And this makes sense because the coronal holes are having open field and the plasma is just trying to come out. Now, what they also do is also consider pixels with only redshift. And for these set of pixels, what they find is that the quiet sun again shows excess redshifts when compared to coronal holes. And finally, if they look at pixels with only blue shifts, they find that the coronal holes now have excess blue shifts when compared to quiet sun. So this clearly is a signature that the solar wind is preferentially starting, or plasma is preferentially moving outwards in the coronal holes when compared to quiet sun. And finally, the clinching result is that if they look at the non-thermal width of the spectral line. So the non-thermal width, for those who may not know, is basically I consider it to be a fudge factor for fitting the excess width of a given line. But then these are sort of related to turbulence, local turbulence during the formation of the line, and they are a representative of the kind of processes that might give rise to the line. So what they find to non-thermal width is that it is consistent across both coronal holes and quiet sun. So the straightforward implication of this work is that the energy deposition process is very similar in both coronal holes and quiet sun. It is only the energy distribution process which is different in coronal holes and quiet sun. In quiet sun, it gives rise to excess redshifts in silicon 4 and excess intensities in silicon 4. But in coronal holes, it gives rise to excess blue shifts. So then a very straightforward question we then ask is, what happens lower in the atmosphere? Silicon 4 was in the lower transition region. We ask what is happening in the chromosphere. So we study the various properties of chromospheric and silicon 4 again as a reference and see what is happening as a function of the magnetic field. Now, the magnesium and carbon line that I've shown here form in optically thick conditions. And this is what a typical magnesium line looks like. So the two peaks are labeled as K2 or H2, and the dip is called K3 or H3. The dip, the central reversal, forms much higher in the atmosphere because it's a self-absorption. and these peaks form much lower in the atmosphere. So the peaks form in the low chromosphere, the dip forms in the high chromosphere. And similarly, you have the carbon-2 line, which is not a Gaussian. So we fit a Gaussian to it, but it is actually not a Gaussian, which is something we show later on in the paper. But on an average, a Gaussian can explain the spectral profile of the carbon-2 lines, but they also form in optically thick conditions, and they also exhibit very complex properties. So we look at the intensity and velocity of these two lines as a function of magnetic field and try to figure out what is happening in the solar atmosphere. Now, a word of note is that the magnesium 2K line was studied in detail. The intensity alone was studied in detail by Pradeep Kashyap and collaborators. But we have taken the K, H line and the intensities and velocities and have expanded on this work. And as I've already mentioned, the silicon 4 line was studied by Durgesh and collaborators, but we have extra data which sort of increases the statistical significance of these results. So first, the intensities with the magnetic field. The silicon 4 intensities is something we know. The quiet sun, now it is orange, shows excess intensities in silicon 4 and compared to coronal holes for regions with similar magnetic field. This is seen in carbon 2. It is also seen in the magnesium features. So these numbers here, 4, 3, 2, 1, correspond to the formation heights. The larger the number, higher it forms in the atmosphere. So what this set of panels means is that it is not just in the lower transition region, but also in the chromosphere, lower chromosphere itself, the differentiation between coronal holes and quiet sun is seen. It is seen only if you account for the underlying magnetic field distribution. And what this basically means is that if you consider a bin of magnetic field, and if you consider two distributions of intensities for coronal holes and quiet sun, as you keep going up in height, the distribution just keep drifting apart till such a level in the corona that these distributions are extremely further apart, and you see that one has low intensity, the other has higher intensity. So very neatly, the picture is set on the intensity differences in the coronal holes and quiet sun. Next, we also look at the average velocities following Durgesh and others. So what we find is, interestingly, in the K2 feature, which forms much lower in the atmosphere, the average velocity is not very different between coronal holes and quiet sun. They are very consistent. And the velocity is like some 1 kilometer per second. In K3, the velocity increases to 2 kilometers, 2.5 kilometers per second. It is again consistent between both the regions. In carbon 2, it is quite consistent, except that at the high strong field regions, you have excess redshifts in coronal holes. In the weak field regions, you have excess redshifts in quiet sun. But on an average, it seems like the velocities are consistent. But note that the velocity scale is very different here. It's 5 kilometers per second here. And finally, in silicon 4, which we have already seen, the average velocity is far more redshifted in quiet sun compared to coronal holes. So clearly, you see that this drifting apart of is taking place between coronal holes and quiet sun. An increasing differentiation is seen as you move from lower part of the atmosphere to higher in the atmosphere. And this is also very well consistent with the fact that these different ions form at different heights, and these are different velocities. So the velocity also increases with formation height. Now this is average velocity. Now we can then ask, what happens if we consider just blue shifted and red shifted pixels separately? Does the magnetic field have systematic effects on the blue shifts and the red shifts in the coronal holes and quiet sun? So first we find that in the coronal holes, in the K3 line, the coronal holes indeed show excess blue shifts when compared to quiet sun, if you only consider blue shifted pixels alone. This is consistently seen in carbon 2 and silicon 4. So if you remember the diagram of 2 with the magnetic funnel coming up, you had some upflows, and these upflows were persisting. This is kind of reminiscent of that. You have these upflows, excess upflows in coronal holes, which are seen in K3, carbon 2, and silicon 4. Now, if you look at the red shifts, it is very interesting. We see again coronal holes show excess red shifts in K3 and carbon 2. It means that plasma is preferentially falling down faster in coronal holes when compared to quiet sun. So this is not something we expect from these results, because this is not something we found the silicon 4. The silicon 4 results which Durgesh and others had, they had excess redshifts in quiet sun when compared to coronal holes. So clearly there is a dichotomy occurring between the chromosphere and the transition region. And this is something that's not quite explainable through just a visual inspection or an analysis. So what we next do is we look at the cross correlation between these different lines. So we look at the flows in the chromosphere, and the flows in the transition region, that is in silicon 4, and look at what happens in the different flows. How are the flows in silicon 4 related to the flows in the chromosphere? So what we basically do is to perform a sum of cross correlation. So what we have is basically, if you can see my video, a bunch of pixels which show both upflows, which show upflows in both silicon 4 and magnesium K3, and look at what the velocities are like, and so on and so forth. So first, if you look at pixels which show downflows in magnesium and downflows in silicon, so it's like that: downflows in magnesium, downflows in silicon. These two are very tightly correlated, which means that plasma which is falling down in silicon is also falling down in magnesium. And interestingly, for a given downflow in magnesium, the downflow in silicon is much larger. And what this means is that there is excess deceleration happening in quiescent when compared to coronal holes in the downflows. Next, if you look at the upflows, so if you have pixels which are showing upflows in magnesium and upflows in silicon, again these are well correlated. And this correlation, and again, and interestingly, now the upflows in coronal holes are much stronger in silicon when compared to quiescent. So for a given upflow in magnesium, the coronal holes preferentially accelerate these upflows to the silicon 4 line when compared to quiescent. Third, if you look at upflows in silicon and downflows in downflows in magnesium, we again find that they are well correlated. And again, the upflows are preferentially accelerated in the silicon line. So what this means, so this is like a signature of bidirectional flow. So you have some plasma which is expanding on both the sides, and you have some downflow in magnesium and some upflow in silicon. And finally, if you look at downflows in silicon and upflows in magnesium, these two have no relation whatsoever. So it's like there are no relations between these two flows. So very clearly, apart from the dependence on magnetic field, we also find that the flows are correlated across the solar atmosphere, which reinforces our assumption, or rather our understanding, that the solar atmosphere is tightly coupled across all the layers. So before we go to the main, before we go to the main models that we present, let us just recapitulate the kind of observations we have had. So first, the intensity differences. The coronal holes have lesser intensity when compared to quiescent. The chromosphere transition region are restricted on an average. This is a well-known result. The average velocity is almost consistent across coronal holes and quiescent in the chromosphere, and the velocity increases with formation height of these different lines, or approximately with temperature. The excess coronal holes exhibit excess redshifts and excess blue shifts over quiescent in the chromosphere, but the excess redshifts are not shown in the transition region, and these flow velocities increase with magnetic flux density. The transition region shows up correlated flows with the chromosphere, and the upflows in transition region are well correlated with upflows and downflows in the chromosphere, with the coronal holes showing larger upflows or larger acceleration of upflows when compared to quiescent. Finally, the transition region downflows are only correlated with downflows in the chromosphere, and the quiescent shows excess deceleration of flows of downflows from the transition region to the chromosphere. So these are the three main results. So if you can see the three colors, there are three main results we have. So we have the intensity result, we have the cross correlation result, and we have the velocity variation with the magnetic field result. So we seek to explain these three results. So first, the cross correlation results. Assume a column of atmosphere where the density is falling with height, and assume that the flow is, we have a flow in the column of atmosphere, but the flow is column mass conserving, column mass flux conserving, which means your rho v is constant. Your rho v is constant and density is falling with height, velocity is increasing with height. So you just need to start some flow at the bottom of the atmosphere, and you just keep accelerating upwards. So if you have an impulsive event, for example, occurring very low in the solar atmosphere, it will drive upflows, or it will drive upflows in the lower atmosphere. And because of column mass flux conserving flows, the flow will just keep going upward in the solar corona. And this will give rise to correlated upflows in all the three lines, or all the lines in consideration.
Vishal, it's 4:45.
Yeah, thanks, Asim. Next, you need not have just the impulsive events in the lower atmosphere. You could have these impulsive events occurring even between the silicon and magnesium formation heights. And in such a case, you will give rise to bidirectional flows. So these bidirectional flows are the ones that we saw earlier in the previous slide, the previous slides. And the plasma that's going upwards can go to silicon and other lines which form higher in the corona. The downflows can keep persisting to cooler and cooler lines. But note that the upflows that you have need not just go as a solar event. It could also just fall down, and while it's falling down, you can see correlated downflows can occur as it falls down because of density increase and temperature decrease. And finally, you could have impulsive events occurring very high in the corona, like the ones we saw for a single pixel in our previous work. So you could have these impulsive events occurring very high in the corona, and that can drive downflows across all the lines. And you see correlated downflows across all the lines. So very elegantly, an impulsive event in a stratified atmosphere can explain the velocity correlations. Now, the intensity differences is something that was explained by Durkesh in his paper with Nived and Sami Solanki. So what they do is basically they look at this result from Wiegelmann and Solanki, wherein so what this plot basically tells is that if you consider a threshold of magnetic field and you look at and you ask what the average loop height, so you assume there's a lot of closed loops, and you ask what the average loop height and loop length are in the Quetzal and coronal hole for different thresholds of magnetic field, and they find that the average loop height is larger in Quetzal when compared to coronal hole. And this plot that I show you here is very reminiscent of the intensity difference plots that I have shown you earlier for various lines. So if you assume that the intensities in different lines as a function of magnetic field is basically a function of loop height, then this kind of a result, it follows from a scaling relation, can explain the intensity differences. Or in other words, you have more open field in coronal holes, which means there is more trapped plasma in Quetzal, and the intensity in Quetzal is larger when compared to coronal holes. But then this is explaining the intensity differences. But what about the velocity differences? So for this, we combine this loop statistics argument with the impulsive heating argument that we presented in the previous slide. So the unified scenario of solar wind emergence and coronal heating that we sort of put forward is that in coronal holes, you have this excess open flux that is undergoing interchange reconnection with various closed loop fields at various heights. And this gives rise to impulsive events that drive bidirectional flows. And the upflows are preferentially accelerated in this open field topology. And what happens, consequence, and the plasma doesn't stay trapped, so it just escapes. And so you have lesser intensity in the coronal holes. A nice consequence of this kind of a model is that this interchange reconnection can give rise to kinked fields, and so you can see this can give rise to these S-shaped structures in the S-shaped magnetic field structures that can propagate outwards as switchbacks in the solar wind. But if this is indeed the case, the flows that we provide in this work will serve as constraints to models which want to have switchbacks somewhere near the solar corona, in the solar atmosphere. And only if these models satisfy the flows that we provide as conditions, can they be viable source of switchback generations. And finally, if you just look at the Quetzal topology, you don't have much open flux here. Predominantly, you have closed loop reconnection. Again, you have the bidirectional flows, but then they are not they are not escaping. The plasma is just filling the loop and making it heat up, and you just see excess intensity. But then, since plasma is already trapped in the foot points of these loops, the deceleration is so when the plasma falls down, there is excess deceleration in these closed loop structures, which is what we also see from the downflow correlation. So the take-home message of this talk is that coronal holes in Quetzal are differentiated in the chromosphere itself, if you account for the underlying magnetic field distribution, and impulsive heating scenario where you have interchange reconnection in coronal holes and closed loop reconnection in Quetzal can very elegantly explain the various observations we have. The major caveats we have are that we need a handle on the numbers. We need to know how much energy, what fraction of energy is going into radiative loss, what fraction of energy is going into driving the flows, so on and so forth. And second, we need the loop scaling relations that we have used may not be valid in the chromosphere, but the extrapolation by and large should be valid. So this whole presentation is based on these 3 papers here, wherein the first 2 have been published in ABJ. The third one has been accepted for publication in ABJ, and for those who know, this was a record acceptance in some 13 or 14 days. And finally, what's next on this front? So as I said, we need exact calculations on energetics. So we are doing some simulations to see if we can get a handle on what these numbers are. And finally, we have been assuming that the coronal holes are the major source of solar wind, but neglecting anything else which might contribute to the solar wind. So there's a separate study we are doing on a deep learning and information theoretic perspective on how much contribution different source regions have on the solar wind. And so I leave you with this slide, which is a simulation of an emerging flux interacting with the background magnetic field and giving rise to the jets that you saw in the first slides. Yeah, so thank you.
Thank you, Vishal. So we have a lot of time for questions. If you have a question, can you please raise your Zoom hand and I will unmute you and you can ask. Yes. Dipanjan, go ahead, please.
Hi, Vishal. Can you hear me?
Yeah, I can hear you, Dipanjan. Yeah.
Yeah, Vishal, fantastic work. Lots of very interesting results.
Thank
It's
you.
a lot of information, so it's still to digest all of it. But I
Yes.
was just curious about the impulsive events that you talked about. And my apologies if you already mentioned about this. Maybe I missed it. So these impulsive events occur at different heights. But what is the nature of them? What is causing this? And why are they reconnection?
Yes.
And so do they and why do they happen at different heights, or this is a random reconnection events? And or what I'm trying to understand is it related to some magnetic field topology that is specific to the particular area?
Yes, exactly. That's essentially the point that we are stressing on here. So in the coronal holes, you have excess open field that undergoes interchange reconnection with the closed loops, and you have these closed loop of different heights. That is a well-known result in the solar atmosphere. So that is going to give rise to impulsive events all over the atmosphere.
Okay.
But in Poisson, you just predominantly you have this closed loop structure, so you don't have the open field to take the mass away.
I see.
Yeah.
I see. So you can also have multiple impulsive events along the same line. Okay.
Yes, you can have them, and that's going to complicate stuff even more.
That will going to complicate things. Okay.
Yes.
Thanks. Very nice
Yeah.
work.
Yeah. Thanks.
Anand, please go ahead.
Okay, can you hear me, Vishal?
Yes, sir. Yes, sir. I can hear you.
I have a couple of questions. Maybe I'll discuss with you later. But one question is that C2 line, you are showing two things. So 1335 is a ground state transition or exact fine structure transition?
This is a ground state transition, I think. I don't remember exactly.
Because I don't remember. So usually around 1335, it is a fine structure state, so it's stronger than the ground state. So I was a bit worried.
I need to check. I think so. The ground state is the same. The excited state from which the transition occurs, they are different. But I need to check what you are asking. I'll check and I'll tell
because
you.
the oscillator strengths are same, but it will have two additional transitions. Because we use it in this, you don't see in absorption at all, and you will see only when you reach a critical density.
I see.
So I was curious about it. Another thing, general point. I understand the philosophy which I used to keep asking Durgesh, and I understood at some stage how you are using different depths and a given transition. But actually, when you say like you are looking at a region, suppose you look at neon 8 transition and you are looking at silicon 4 transition, what you are saying is that you have in a simple physics wise, there you have a cylinder of gas, maybe with different density temperature combination. Your tracers peak at different locations, right? It is not that because slightly misleading when you are talking about silicon 4 and Mg magnesium outflowing correlation and infalling correlation. You see, the way I can think of is that there is a column of gas which is actually outflowing. If it is outflowing, the highest density regions will be picked if you look at Mg, Mg2 or whatever, and the low density, high temperature will be picked by silicon 4. But it is not that silicon 4 ion is moving with different velocity compared to magnesium ion, right? Because these are just everywhere. There is no species segregation, right?
Yes,
basically, like they are as they travel outwards, their physical state is changing, and because of which different transitions become brighter or fainter or whatever, right?
That is true.
But in general, I would expect even if you take Saha equation or any of the collisional equilibrium, there is a width to the temperature delta.
Exactly.
T.
Yes.
So is that not important in your case?
So that so that is what we call the contribution function for different ions, and by and large these are like very sharply peaked in log T. So we just assume that the ion forms at a particular temperature. It's a misnomer. I agree that it's a misnomer to say it forms at one temperature. There's a range of temperatures for a given density structure it forms, but contribution function is very sharply peaked and falls down. So that's why
I think the other way of asking the question is that why do you expect there is no correlation between these two tracers? Because basically, if I have, I am
Between these two
sending a
tracers?
fluid which is magnesium or
magnesium forms in optically thick conditions. It forms much lower in height.
No. But what I mean to say is that these are tracers of. Suppose if I send a jet or wind towards you, and with an idea that a density temperature will change as the gas move, so I will consider as if there is a gas particle which is moving.
Right.
The gas particle has both magnesium and neon 8 or whatever silicon, everything, neon, magnesium, silicon are there. But when it is very close to your photosphere, the density temperatures are such that only silicon 4 will peak in the emission. That will come from there. Whereas the gas move outward, the silicon 4 will become silicon 5, 6 or whatever. Whereas the other ions will come. So I would think this is some sort of a sequence of events. So if you are looking at a region, unless otherwise you are thinking of, so what you are saying is that there is no gas which is sort of stationary. If, for example, if you say that silicon or magnesium 2 belongs to, it's not belong to the jet, it is belong to the photosphere, then you don't expect any correlation between them.
No, there's a lot of dynamics going on here. There's almost no plasma that is just sitting there, doing nothing.
That is why I'm saying that the picture, at least for an outsider, I would like to confirm this. I am thinking that there is a gas which is flowing out.
Right.
At different locations, it will emit different lines.
Yes, that is true. That is correct.
And I don't expect, if that is the situation, as you are rightly saying, that there should be correlation between these quantities, right?
There should not be, or there should be.
Something is blue shifted, you expect other thing to be blue shifted.
Yes, that is the thing. But here is the thing.
If you are finding anti-correlation, then you are summing over contradicting flows, right? In the sense.
No, so the assumption is that if you have a cylinder of plasma, the whole of all the plasma is flowing towards you. Let's say, then you would say correlated flows across. So different lines would be characteristically emitting from different columns of different slices of this column, right? But what if you have a flow that's coming from both the sides, and both these sides are, so velocity on this side is well correlated with velocity on this side, and you have characteristics, so that, and the density structure on these two sides is very different. So magnesium predominantly forms here, let's say, or predominantly emits on this side, and the carbon or the silicon is predominantly seen on this side. So then you expect an anti-correlation, which is what we are also seeing.
So I think I'm getting confused. Maybe we can discuss. We don't want to.
Sure.
We can discuss over tea.
But the thing that you
confused. See, if you discuss the whole thing in terms of density, temperature, it becomes much easier. So you have density, temperature, velocity of the fluid, and if you say that there is a regular gradient along your line of sight, you will find correlation.
Yes.
But if you see that preferentially you have high density gas falling in and low density gas going out, you will find relatively, I'm saying, falling in means like moving slower compared to the.
Exactly.
So I think this is where my confusion comes. We can discuss this because in the end it is one fluid only. It is
exactly.
Simple fluid.
So the simple picture that you have there now, the column of plasma is that expanding flux tube structure that I'm showing here in this slide. So you see this blue shift there, that is from silicon 2, I think. And you see that blue shift persists in neon 8 also traces that blue shift. So that is the kind of correlation that you are talking about. But the bidirectional flow is something that we are seeing. It's also seen in simulations. We can discuss this later, maybe.
Yeah. Okay, Kandu. Kandu, you're.
Yeah. Sorry, I couldn't unmute because I think permission wasn't there. Can you hear?
Yes, sir. Yes, sir. I can hear you.
So every time I hear your talk, I find something different, which is interesting. But it's, it's fantastic. I think your talk was excellent, except that you have to keep on exactly locked on to your talk. Otherwise, you go, berserk in some sense.
Yeah.
My questions are the following. One is to do with what is the time scale over which you make any one of these observations? Is it very small compared to
30 seconds? The rastering time is 30 seconds for each slit, the spectrum from each slit.
Right. So when you're thinking about any of these things, it's very small time compared to, let's say, the solar cycle time, I guess.
Yes, absolutely. Yes.
So what happens if you look at different parts of the solar cycle. I mean, we'll have such studies where you look at the sun, I mean, the same sort of stuff when you have either solar maximum compared to minimum and all that stuff.
You read my mind, actually. This is something I was telling Durgesh, we should do it. So similar kind of analysis across various parts of the solar cycle. But one thing is this, the coronal holes are not predominantly seen during the maximum phase, right? So, I don't know.
Toroidal loops which are probably coming out.
Yes.
So things are all confined a bit more.
Yes.
The maximum.
Yes.
And the minimum, probably there are more open field lines.
Yes. Yes.
That's certainly true. So this is one thing. Second thing which I came to my mind is that, you see, at least when you come from the dynamo perspective, there's a lot of things to do with magnetic helicity.
Yes.
And one of the ways in which at least some of us believe the dynamo works is by shedding magnetic helicity of some kind or the other from the interior into the corona or something like this.
Right. Right.
So this is, I mean, there's some which, now what are the signatures of such a shedding? Of course, there are people generally point to CME's, coronal mass ejections, as a thing which could take out stuff. But even in the quiet sun, I mean, the magnetic field is not going to, I mean, there is a random field, there may be a small average field also.
Right.
So are there specific signatures of helical fields coming out is what I was, maybe it's dominated by your braiding. So your braiding also is generating all the time helicity. I don't know, maybe Nishant also has some idea about such a thing.
That is true. So these, the first couple of observations I showed of jets, right? So there was one jet that was like, going like tornado. So that I think was due to this thing. So this one, the one on the left side. So the thing was going, so you can see the helical motion. So that was due to untwisting of the emerging flux region. So I think Mark or somebody showed in their papers that this kind of a thing occurs.
Okay.
So, but this is an active region. This is not in quiet sun. But
I mean,
I don't know. I have to check that. But I think we don't. So the quiet sun fields, the error bar is like some 10 Gauss. If you take 100 Gauss field and some 10 Gauss errors, I don't know how good the helicity computation could be for bipoles, let's say.
Yeah, I mean, I think, of course, Nishant will know much more, that you try to compute the helicity in this surface regions. But I'm probably thinking about some correlation between what is there and what you see in terms of active things going on, which are ejecting plasma and all that kind of stuff.
I see.
Okay, one can talk.
We can think about it. I don't have much idea on how this could be.
Very interesting talk. I would have been happier if you had, slightly taken 10 more minutes.
Okay. I was having my time on mobile, so I was trying to be on time.
I see. That's fine.
Yeah, sure.
Thanks a lot. Thank you.
Yeah, thanks.
Durgesh, go ahead.
Yeah, I just wanted to add a couple of things to Kandu. Regarding the helicity, people have done a lot of calculations for, as Vishal also pointed out, for active regions, but the errors in the magnetic field measurement, particularly in the vector field, is so large that the helicity computation becomes very, very difficult. So they don't actually get anywhere with that. Second, about the first question you asked, Kandu, about the solar cycle thing, I don't think it should make a difference, because if you, I mean, our studies will be much easily done if we are looking at somewhere near rising phase or just declining phase of the solar cycle, because we will have more coronal holes on the disk rather than on the poles, because at solar minimum you see coronal holes only towards the poles, and that's where the magnetic field measurement is not very good. So we wouldn't see during solar minimum very much anyways. But people have looked at the properties of coronal hole in general during minimum and maximum, and they don't really find much difference in the overall general dynamics. So I think what we are doing here, that should not make a difference depending on which phase of the solar cycle you're looking at.
Okay, yeah, okay, yes, fine. Yeah, thanks, Durgesh.
Yeah, thanks.
Okay, so I don't see any more hands up. In which case, let's thank Vishal for an interesting talk and an interesting discussion. And use your Zoom clapping hands to show your claps. And we'll see you for the next session of the seminars and colloquia. Okay, thank you, everyone.
Yeah, thank you. Bye.